All right, two athletes compete in a two-event competition, shot put and the long jump. Chris threw the shot put 63 feet, and Ryan threw it 66 feet. Chris jumped 27 feet, 3 inches in the long jump, and Ryan jumped 27 feet. Is Chris or Ryan the better athlete? So a couple things that we're looking for here, and the reason that you have like a whole page, obviously, is because we're going to be writing a lot down. So we're looking for which athlete did better overall compared to his peers. We are going to use standard deviation to show how far the value is from the mean. And then we're going to express values in terms of standard deviations because it standardizes the values. I'm not sure why these numbers aren't in the boxes, but the mean for shot put is 60 feet. For a long jump, it's 26 feet.
Is that just standard? Is that like what it...
No, it just should have been given to you, and
Okay.
it didn't put it in the box for some reason. Standard deviation, 3 feet. And standard deviation for a long jump is 6 inches, which would be 0.5 feet, obviously, so just that everything's in the same units. What is 27 feet, 3 inches if we translate everything into feet?
Wait, what is what?
3 inches is how much of a foot?
Oh, 1/4?
2.5.
So 0.25. So 27.25 feet. We're just going to want that number to reference. We can't have something that has like multiple units when we're doing this stuff. It's not going to work.
Is there anywhere in stats that would work or no? Does it always have to be like the same unit?
It's going to have to be the same units.
Okay.
It's not going to work otherwise. All right, I'm just going to draw a normal curve so that we have it for reference. So the mean is the middle value here. And then we have 1, 2, and 3 standard deviations. What was our formula for z-score? It's the very first one from the notes yesterday.
Like, what's the formula?
Yes.
Z equals y minus y with the mean of the distribution over standard deviation.
Y minus y bar over s. All right, so now I'm going to use that and calculate the z-score for each person in comparison to all the people in the competition. So I'm just going to do this as, like, I'm going to say Chris and Ryan. And then I'm going to do first shot put. And then we'll do long jump. All right, so the first one for shot put for Chris is Z equals, what was it, 63 feet. So 63 minus the mean of 60 divided by the standard deviation of 3, which ends up being 1. So that's 1 standard deviation above the mean. For Ryan, it was 66 feet, so 66 minus 60 over 3, which ends up being 2 standard deviations above the mean. I'm gonna do long jump in a different color so it doesn't run together so much. So then the long jump for Chris, Z equals 27.25 minus 26 over 0.5. That ends up being 2.5 standard deviations above. Then for Ryan, Z equals 27 minus 26 over 0.5, which is 2 standard deviations above the mean. So based on that, who's the better athlete? Why?
Because I don't know if it's like mathematically accurate, but like if you add up the SB for Chris, it's only 3.5, but for Ryan, it's 4. I don't know, that's like the way it's.
Yeah, or if we took the average of the two of them, 3.5 or.
So just whatever the SD is, like you just combine those and that's gonna be, that'll tell you if it's bigger or smaller.
Well, I would say take the average of them if we're comparing multiple things like we are in this one. So I would say like 1 plus 2.5 is 3.5 divided by 2, which is like what, 1.75. And then whereas for Ryan, 2 plus 2 divided by 2 would be 2, and so his would be higher.
With them being like, if it was like below the mean, would that change anything, or would we just still take the average of all that?
No, it would be a little different.
Okay.
But typically if you have one that's below and one that's above, the one that's above is who you're gonna. And I mean, the other thing is like Ryan is consistently higher, like 2 standard deviations above the mean, whereas Chris was for the long jump, but he was not even close on the shot put.
Yeah.
So it's kind of like, to some extent, it's just kind of like looking at it and being like, okay, this makes sense this way. So
And so like as long as you can explain it, then you're fine, right? It's
more or less. I mean, it has to make sense, but.
right.
All right, next page. A statistics class took a 40-point quiz. Results show a mean score of 30, a median of 32, an IQR of 8, a standard deviation of 6, a min of 12, a Q1 of 27. Suppose your score is a 35. What happens to each of the statistics if I decide to weight the quiz as 50 points and we'll add 10 points to every score? So originally, and this is going to be all the way down, or the original like Y value. So like you can go ahead and fill out the top row all like across. So our score was a 35 to start with. The mean was 30. Median was 32. IQR was 8. Standard deviation was 6. Min was 12. And Q1 was 27. Now, I don't need Q3, but could I find Q3 with my given information? How?
By saying like IQR is equal to Q3 minus 27, and then there's like new.
Yep.
I was gonna sound really stupid, but that says originally, right?
It's original Y.
Okay, that's what I thought.
Yeah, like the original Y value.
That's what I thought, but then I was looking at it and I was like, maybe I should ask, because I like.
Yeah, well, I initially said originally, and then I was like, because I was saying, like, what were, like, the original values, and then I said originally, and then I was like, wait, no, I'm supposed to say original Y value.
Yeah, I figured it out just because, like, you only had one L, and I was about to ask about that.
I'm just really bad at spelling.
Yeah, that's what I was
She's a
wondering.
math person.
Right, not an English person.
Yeah. So we're going to go through and look at each of these, and then we're going to kind of make a summary at the bottom. I actually might summarize a few things first, because otherwise I feel like mathematically you're going to end up with the wrong answers. I don't know.
If I decide to lose weight, the quiz is 50 points. So are we like? So if it went up by like from 40 to 50, that's a 25% increase, right? Am I thinking about this the right way? Is that not the way
No.
to think about it? Okay. All right.
I'm going to go down here and do the summary part first, because it's not directly, I mean, it's related to this, but you need to know this information to be able to answer these questions, so I'd rather just go ahead and give it to you instead of having to, like, say everything twice, if you will. So if we add the same number to each value, so adding the same number to each value, changes the center, and individual values. So when I'm saying that, I mean the mean and the median. They are changed by whatever that number is that I'm adding. So if I'm adding 25 to everyone, then I add 25 to the mean and the median, so on and so forth. Individual values like our Q values, like Q1, Q3, min, stuff like that. But not IQR, or not spread, IQR and standard deviation. And you'll kind of see why it's that. Like, it will make sense, but people get really confused about this to start with. That's why I was like, let me just go ahead and summarize this from the beginning. When you add something to the numbers, because you're changing everything by the exact same amount, that's not going to change the range of your, like, IQR or your standard deviation, because everything is changed by the exact same amount. However, multiplying every value by the same number changes the center and individual values meaning the mean and the median. So we're multiplying every single value by that multiplier. However, in this case, it also changes the spread. So IQR, and standard deviation. So multiplying, everything gets multiplied, adding and subtracting, just not our spread type values. All right, so going back up to the first one. The quiz is originally 40 points, but now it's 50 points. So I add 10 points to every score. So this is going to be y plus 10. So that means that instead of a 35, you got a what? 45. So instead of a 35 out of 40, you now have a 45 out of 50. So what is the mean then?
Just add 10. Okay.
Yep,
40.
just add 10. So 40. What about the median?
42.
What about IQR?
18. Oh, wait, no, it's going to be different, right? Same for everybody. But not spread. So it's just going to stay the same?
So it stays the same.
Okay.
Because all the values are changing by the exact same amount.
Okay.
So standard deviation would also be the same. So it would be 6. What about the min?
Is that still 12 or is that getting added?
Any individual value like that, everything, it's being added to.
Okay, so 22.
And Q1?
37. Wait.
Yep.
Okay. So basically everything's going to change the same when you're doing an adding one except the IQR and standard deviation?
Yes.
Okay.
So that one pretty easy. Part B, what happens to the statistics if I weight the quiz as 80 points and I double each score? So basically, instead of it being out of 40 points, it's out of 80, so I took and I doubled the score.
So now everything changes, right?
So now it's 2 times y. Yes, everything changes. So my score is now what?
70.
The mean is
60.
median,
64.
IQR,
That's
16?
same too.
16. So when it's multiplying, we multiply everything. If it's adding, it's not the spread.
That's kind of easy.
Standard deviation,
12.
min,
24.
Q1.
54?
So individually, not too bad, right? However, now what happens if I weight the quiz as 100 points and so I double each score, then I add 20.
So you'll only do the multiplying part with all of it?
So my equation is going to be 2y plus 20. So essentially we're plugging the numbers in, but now that I have the adding factor, what do you think is going to end up happening when I get to IQR and standard deviation?
Only multiply?
We're just going to multiply.
Okay.
So what happens with my score?
They double, yes, 90.
And you can take, obviously we've already doubled the numbers up here, so the ones that you need to add to, you can just, add them. So the mean is
80.
median,
84. 16?
Yep. That stays the same. Standard deviation.
12.
Yep, that one also stays the same. Min. 44 and Q1. 74. So not too bad, right? You just kind of have to think about what you're doing if you're, like, when you have a problem like this.
Don't rush it.
Yeah, don't, like, you know, problems like this are meant to be, like, easy money points, right? Like, that you're hopefully are easier and able to get the most points for. All right, this next problem's not as long as the fact that I gave you a whole page for it. That was a little bit excessive on my part. You will use a decent amount of the page, but I didn't need, I mean, I will write a decent size, I feel like, and I didn't use a full page, so. All right, Martha scored 80 on a physics test where the mean was 75 and the standard deviation was 5. Bob scored 83 on a chemistry test where the mean was 73 and the standard deviation was 12. Who scored the highest relative to the rest of his or her class? Show your work and defend your answer. So I like to start out with a picture. So I'm going to do 2 normal models using the mean and standard deviation for each one. So for the first one, for Martha, I'm going to do a little normal model. The mean for the class was 75 with a standard deviation of 5. So that would be at 80. That happens to be her score. So that kind of works out nicely. I could keep going with my normal model and increments of 5 and get 3 standard deviations away, but I don't need to do that. Then for Bob, he scored an 83 with the mean being 73 and a standard deviation of 12. That's not it.
When you said you were drawing a picture, I thought you were going to draw up like 2 different tests.
No. Very different types of drawing pictures in here. So 1 standard deviation away would be at 85. But his score was an 83, so I'm going to just draw that in kind of tiny there, just for my reference. Now, just by seeing the picture, who scored higher relative to their class?
Mark. Wait. Yeah, no, Bob. Never mind. Not Martha.
Martha.
It was Martha.
But we're going to show mathematically how that worked. So, Z score over here for Martha, her score was an 80, minus the average was 75, over the standard deviation of 5. So that ends up being 5 over 5, which is 1. So 1 standard deviation above. Bob's, though, his score was an 83, mean of 73, with a standard deviation of 12. And that comes out to like 0.83. I think it's repeating, something like that. What I have written down is correct. And that's standard deviation above. So while they both did better than the rest of their class, Martha did better relative to her class. Her score was 1 standard deviation above the mean, but Bob's score was only 0.83 standard deviations above the mean. So I've essentially shown work 2 different ways and then summarized it up. This next problem, if you just want to make note of it, it is number 17 in the book. And I think I assign you, I want to say it's like a couple problems after that that are connected to this problem. So I want to say it's probably like 19, 21, maybe 23, something like that. But this is number 17. So if you get to a problem for homework that's like, refer to number 17, this is number 17. All right, so the Virginia Cooperative Extension reports that the mean weight of yearling Angus steers is 1,152 pounds. Suppose the weights of all such animals can be described by a normal model with a standard deviation of 84 pounds. How many standard deviations from the mean would a steer weighing 1,000 pounds be? So I set up my z-score value. So 1,000 minus the mean, 1,152, divided by standard deviation of 84. And just to eliminate us having to do this, it should be about negative 1.81. So a steer weighing 1,000 pounds would be negative 1.81 standard deviations below the mean. You don't want to say negative 1.81 standard deviations below, because it's kind of like an oxymoron. So obviously we got a negative when we did the z-value, but when you're writing the summary, you just want to say below the mean instead. So then the follow-up question is, which would be more unusual, a steer weighing 1,000 pounds or one weighing 1,250 pounds? So we've already found for 1,000, so I need to now do a z-score for 1,250. So how would I set that one up?
E equals 1,250 minus 1,152 divided by 84.
Yep. And this comes out to be 1.17. So, which is more unusual?
The 1,000 pound one.
Why?
Because it's farther away from the mean.
Yep, the 1,000 pound is farther from the mean. So the steer weighing 1,000 pounds is more unusual because its z-score is farther from the mean than the steer weighing 1,250 pounds. All right, we're going to do one more page, and then that'll be where we stop for today. If we don't have time to answer your questions, Chris, we can do that at the start tomorrow. Just remind me.
Okay.
I'm going to try to give y'all time on Friday to be able to work on this, so I'm trying to get through it. So. All right, so you'll notice that these examples start back at, like, number 1 again, and that's because the people that, like, wrote these, like, I have, like, worksheets that people had written, and then I just, like, pull from it or whatever, but they did things in days, and so this was, like, day 2, problem 1. but I don't really do it based on that. So if numbering's ever weird, that's typically why. So, anyways. All right, so the Environmental Protection Agency, or the EPA, fuel economy estimates for automobile models tested recently predicted a mean of 24.8 miles per gallon and a standard deviation of 6.2 miles per gallon for highway driving. Assume the normal model can be applied. Draw a model for auto fuel economy. Clearly label it. Show what the 68, 95, 99.7 rule predicts about miles per gallon. So that is the empirical rule, 68, 95, 99.7. And so I'm going to start out by drawing a normal model. I'm spreading it out a little bit just because I need to have plenty of room to write. Oh, good. So these values down here are going to be the highway mileage in miles per gallon. So the mean value they tell me is 24.8. And then I have a standard deviation of 6.2. So that means that I'm going to add 6.2 3 times to get 3 standard deviations in the positive direction. And then I'm going to subtract 6.2 3 times to get it in the negative direction.
Do you just always do it 3 times?
Yeah, because we want 3 standard deviations. So in total, you should have 7 numbers on
But you're doing what 3 times?
a normal model. I'm going to add 6.2 to the previous number.
Okay.
So 24.8 plus 6.2 is going to be 31. 31 plus 6.2 is 37.2. And then 37.2 plus 6.2 is going to be 43.4. So that's 3 standard deviations in the positive direction. Now going the other way, subtracting it off. 24.8 minus 6.2 is going to be 18.6. 18.6 minus 6.2 is going to be 12.4. And then 12.4 minus 6.2 is going to be 6.2. So then I'm going to go through and label this 68, 95, 99.7 rule. So from in the dimensions of being 1 standard deviation away, that is 68% of our data. And so I just do it like that. 2 standard deviations away is 95% of our data. And then 3 standard deviations away is 99.7% of our data.
And that's always true? Like a
These percentages, yes.
okay. So that's only if the graph's like symmetrical though, right?
Well, it's a normal model, so it has to be.
Okay.
All right, so in what interval would you expect the central 68% of autos to be found? So the nice thing about already having the picture is I already know the answer to that question. It's going to be 18.6 to 31 miles per gallon. What percent of autos should get more than 31 miles per gallon?
Maybe both of them, the 95 and the 99.7.
Well, it would be total percentage that's out here.
Out of 100. So would it be like?
Are you like subtracting 6?
But I can't just subtract 68 from 100
97.
because out here I still have stuff then that's not being accounted for. So what I do is I take 100. I'm going to subtract off 68, which means that I now have all this data that I'm currently covering up with my hands left over, right? Which is what, 32? So I only want the right side. So what might I need to do then?
Cut both.
Divide it in half. So 100 minus 68 divided by 2, which is going to be 16% of the data.
So 16% of cars should get more than 31 miles per gallon.
Yes.
Okay.
Now the next question, it's similar, but it is a little bit different in how it's worded. What percent of cars should get between 31 and 37.2 miles per gallon? So what do you notice about like those values when you look at it?
The between 68 and 95%.
Yep. So what do you think I might need to do?
Subtract 68 from 95.
So if I do that, that means I'm left with this value, these two values here, where my index fingers are. But I only want this side. So what do I need to do?
Divide by 2.
Divide by 2.
So I was right. Is it 8%?
No. Because it's 95% minus the 68%. So 95, because I'm looking at 37.2 being my upper, 68 being the lower, divided by 2, and that is approximately 13.5%. It's not exactly, it's a
close.
rounded number.
I'm like a little confused. Why did we use like 100 for C, but we only used like up to the 95 on D?
Because of what the question asked for.
So just all in general.
So this one said, what percent should get more than 31 miles per gallon, which is all the way up to like 100 miles per gallon or whatever. This one says between 31 and 37.2. And 37.2 is at 2 standard deviations, so it's 95.
Okay.
Describe the gas mileage for the worst 2.5% of all cars. So this one's a little weird, and people tend to get confused about this one. So the worst 2.5% of all cars would be where? Over here somewhere, right?
Yeah.
Now, 2.5% is somewhere in this range, but I need to know the exact value. So any ideas what I might need to do with that 2.5%? It's kind of doing a reverse of what we did in the last two questions.
Would you do like? Can you do like 100?
Pretty much do exactly the opposite of what we did in the last question.
2.5, like would 2.5 be the what it equals? 2.5 equals 100 minus something over 2.
You're kind of on the right track. So 2.5, if I double that, that gives me 5%. 5% would
Why
be
did you
what?
double it?
Because right now I only need, or it's only giving me this half, but I don't have any of these percentages that only give me half. So I need to double it so that I've accounted for both sides.
Okay.
So then which one would make sense if I had the 5% value which percentage that's on my thing would make sense to go with 5? 95. 95 plus 5 is
100.
100. So that's why. So 5%. So because it goes with that, I know that this half then is my 2.5% that's the worst. So that value is going to be 12.4 miles per gallon. And I want to specifically say less than 12.4 because the worst 2.5% of all cars would have less than 12.4 miles per gallon. The reason I was saying work backwards was I was trying to get you to multiply by 2 to like invert the process. So that's why I was saying it that way.
I was thinking that, but I was like, I don't know what I'm doing. I'm just gonna say something random.
All right, what should you consider to be unusually high miles per gallon and then unusually low? So what do we consider unusual?
Anything like because of the jump from like 68 to 95.
More than how far away?
More than some. Wait.
2?
More than 1. 2.
Same.
Okay.
More than 2.
Okay.
So more than 2 is unusual.
So more than 37.2.
So more than 2 standard deviations is what we consider unusual in either direction. So on the high side, so high would be approximately 37.2 miles per gallon or more. That would be unusual. On the low side, what would it be?
12.4, right? Or lower?
Yep, 12.4 miles per gallon or less. So, obviously we don't have a lot of time, but the reason I was going to stop after this page is because the ones tomorrow, there's a way we can do some of it by hand and then also a way to do it on the calculator. I'm primarily going to do the calculator method because obviously it's easier when the calculator does stuff for you. But we may not finish this all tomorrow, but it'll be close, and then hopefully Friday we'll be able to wrap it up, and then y'all have time to work on the problems to go with chapter 6. But yeah, just remind me at the beginning tomorrow so we can look over those questions.
Okay.
Do you know which ones it is so I can look over them? Find my sticky note.
I think it's like parts of like all. Well, okay, 7 makes sense. I think 19 started to, but then I just was like, there's so many like outliers. It's like confusing a little bit. 23.